Hello everyone, and welcome to the new Oxford Discrete Maths and Probability Seminar. My name is Christina Goldschmidt. It's great to see so many of you out there. Since this is our first session, I think a few announcements are probably in order. So you'll have noticed that we've muted you all, but you can have your video on and off as you please. Unless this turns out to cause technical problems, we like having the possibility so that you can have it on so that in particular the speaker has an audience to speak to. In order to ask a question, you can raise your hand. So in order to do that, you need to click in participants and find your name on the list. And then one of the options that you're given is raise hand. We will try to monitor that list so we can see people trying to ask questions. We'd like to encourage you during the seminar to ask any questions that you have, in fact, in the chat box rather than by raising your hand. And if you know the answer, you should, of course, feel free to give it. We'd also like to encourage people to ask questions about how you use Zoom in the chat box. I'm sure there are people out there who know much more than me about this, and I'm sure we have the knowledge collectively to be able to sort problems out. In this way, we hope to keep interruptions of the speaker to a minimum, because in this format, it's slightly difficult to deal with them. We will monitor the chat, and anything that we feel needs an immediate answer, we'll raise with the speaker on your behalf. We're recording this seminar and we're going to put it on YouTube for an indefinite period. Only the slides and whoever's currently speaking will be recorded. But if you don't wish your personal data, i.e. your username, your video or your audio to be recorded, you won't be able to ask any questions. If you're happy to contribute to your chat under your own name, that's actually really useful. You can change your name by clicking on participants and following the relevant button. We've set up a mailing list, as many of you already know, and you can see from the slide how to subscribe to it. Depending on how much of a problem Zoom bombing turns out to be, we may need to use it in order to distribute Zoom links for subsequent seminars. So it'd be really helpful if you could sign up. In future weeks, we're intending to have 2 seminars with a gap in the middle so that people can catch up in the chat. You have the option of sending private messages or messages to the whole of the audience, or go and have a coffee. And we're going to try to take the opportunity in the coming weeks to experiment a bit with the format, what works, what doesn't work. In that line, any suggestions are hugely welcome. Please email both me and Alex Scott. Our email addresses can be found from the seminar webpage. And without further ado, I'm going to hand over to Alex. Who needs to unmute himself.
Try again. Okay, now I should be unmuted. So welcome again to the first Oxford Discrete Maths and Probability online seminar. Looks like we have a great turnout. I put up the webpage in the chat, and Rob's slides are available on the webpage. So they should also come through Zoom, but if you want an independent copy to flick through, particularly if you have a poor connection, then you can download them from the webpage. Okay, let's get on with the maths part. So it's a great pleasure to welcome Rob Morris, talking from Brazil, from IMPA. He's our generous guinea pig for the first talk, and it's delightful to have him. So without further ado, let me hand over to Rob.
Okay, hopefully that's working. Right, thank you very much, Alex. Thank you very much, Alex and Christina, for the invitation to speak. Great pleasure to be with you. This is my first time giving a seminar like this, so please be gentle. I'll do my best. Oh, please, yeah, I mean, okay, you're supposed to ask lots of questions in the chat, but I'm very happy to have questions sent to me as well. Okay, so I'm going to tell you about something called Erdős covering systems. I'll try and introduce these gently in a minute. So this is joint work with Paul Balister, Béla Bollobás, Julian, Sahasrabudhe, and Marius Tiba. And it's an appropriate thing to talk about in Oxford because some of the key ideas that I'll be trying to explain to you were introduced by Robert Hough, I think when he was a postdoc in Oxford. Okay, so what is a covering system? I should say we'll start out with something that looks kind of number theoretic, but it will fairly quickly become something that looks more combinatorial, and there will be some probability in there as well. Okay, so it's nothing more than a finite collection of arithmetic progressions, infinite arithmetic progressions that cover the integers. So Erdős was interested in covering systems with distinct moduli. So it's easy to cover the integers with, if you're allowed to use the same modulus more than once, you can just take, say, 1 mod 2 and 0 mod 2, or everything mod the same number. It's also not too difficult to find a covering system with distinct moduli. Here's a simple example. And I just want to go through this one, spend a couple of minutes on this. I want to sort of explain how you should think about such an object. So note that all the moduli are divisible by 12. So we should work mod 12. And I'm going to draw mod 12 like this in 2 dimensions. So Z4, whatever's on the bottom, and Z3 is the vertical axis. So here are the numbers. So the columns are 0, 1, 2, 3 mod 4, and the rows are 0, what am I saying? 0, 1, 2 mod 3. And so what do we do? So first we knock out everything at 0 mod 2, which looks like that. So you can see it's a rectangle, which is quite useful. And next we're going to knock out everything that's 0 mod 3. That's the bottom row. Then we knock out everything that's 1 mod 4, which is the second, what's left in the second column. Then we knock out whatever's 5 mod 6, which is that guy. And finally, we knock out 7 mod 12. And we knocked out everybody. Okay, so we're going to see this picture again later on. So we should think of working modulo the least common multiple of all of the moduli, and we're going to break it up into this sort of this high dimensional cube using the Chinese remainder theorem. So, okay. So what was Erdős's motivation? He, not exactly this one, but another very simple covering system. He used it to answer a question of Romanov. So I said, showing that not all odd numbers are the form 2k plus p. Okay, so Erdős introduced these, and he has lots of questions about them. So the first questions and most famous questions about these systems were asked by Erdős in this initial paper when he answered this question of Romanov. He said, do there exist covering systems with distinct moduli and all moduli arbitrarily large? So the one we just saw had a modulus 2. So can you get rid of 2? Can you get rid of 2 and 3, and so on? Another very basic question, how many minimal covering systems of size n are there? So how many are there? So minimal is necessary, as we'll see on the next slide, otherwise there's infinitely many. And here's a slightly more complicated question. So yeah, minimal will be defined on the next slide. So I'm going to ignore the chat now. So it's a slightly more complicated question. So suppose you take the moduli in the interval n up to constant times n, then do you miss a set of density at least delta? This was asked by Erdős and Graham in 1980. So this will also motivate our some of the questions we look at a little later. And one thing you should notice about this is that the sum of 1 over d for d in this interval is bounded. That's worth remembering for later. Okay. Ooh. Here we go. Okay, so we'll start with this counting question. Partly because it's nice and combinatorial, and partly because it'll give me a chance to give you a feel for what these things look like, or what they sort of typically look like. So Erdős gave a simple proof that there are only finitely many of these. This is in a paper in Hungarian a couple of years after his original paper. This is a very nice exercise, so I encourage you to try and prove this yourselves. So he gave a doubly exponential bound, doubly exponential on n. So note that you need minimal. So minimal just means that if you remove any arithmetic progression, you don't cover anymore. Okay. So notice that if you don't have minimal, then you could just cover, and then you just add any kind of arithmetic progressions on top, and you have infinitely many choices. So it's sort of silly. So the ones you're interested in really are the minimal ones. Once you've covered, then you can do whatever on top. So for example, you could just cover with Z and then take anything. A very nice theorem was proved by Simpson in 1985. He showed that the largest modulus in such a system is size at most 2 to the n minus 1. And this is best possible because of this system. So this is taking 1 mod 2, so that leaves the evens, and then 2 mod 4, which leaves 0 mod 4, and then 4 mod 8, which leaves 0 mod 8, and so on. And at some point, you just stop and cover 0 mod 2 to the n minus 1. Okay? So this is a very simple example of something that we'll, in the next slide, call a frame. And note that if all n are at most 2 to the n, then there's only 2 to the big O n squared choices. So this bound is much better than Edge's bound. Edge's bound was like 2 to the n. So Simpson got this down to 2 to the n squared. Though he wasn't thinking about that problem, but it follows immediately from his theorem. Okay, so that's an upper bound. What about a lower bound? So how can we construct lots of these things? Well, let's try to generalize this this example that showed that Simpson's result was optimal. So I should say Simpson proved a more general theorem for which the objects I'm about to describe were also the extremal examples. So I should say, perhaps Simpson, or perhaps this is folklore, generalizes as follows. So let's look at the first k primes. So our least common multiple is qk. And then, okay, this looks a bit complicated, but I'll try to explain. It's quite simple, really. So choose an arithmetic progression. So for each prime and each 1 up to p minus 1, so choose p minus 1 arithmetic progressions for each prime that cover basically all but one of the congruences mod p. We'll see an example on the next slide. So we're going to cover one thing mod 2. We're going to leave behind is everything that's 0 mod 2. When we move to prime 3, we cover 1 mod 3 and 2 mod 3. We're going to leave 0 mod 3, and so on. And this is just something that does it. And notice the only thing we're choosing here is the d. So we're choosing for each progression, we're going to choose a d that divides qi minus 1. There's going to be 2 to the I minus 1 choices. Okay, and it's not too difficult to see that together with 0 mod qk, these cover z. So again, I'll show an example on the next slide. Okay, and we're going to call these things frames. Okay, so let's just go through this a bit more slowly. So what does a frame look like? So for p is 2, there's no choice. We just take the odds. Okay, so that's the first arithmetic progression will always be 1 mod 2. For p equals 3, then we can have a choice. So if a equals 1, we can take 2 mod 3 or 2 mod 6. And either 1 mod 3 or 4 mod 6. And so we've covered all the odds mod 6 with the first progression. And now we cover everything that's 2 or 4 mod 6. And we're left with is everything that's 0 mod 6. Okay, so we're left with just things that are 0 mod 2 times 3. And then for p equals 5, we do something similar. So we're going to pick 4 progressions covering basically 1, 2, 3, and 4 mod 5. And here are the examples. And because there are 4 different Ds we can choose from, then we can do this with distinct moduli. If equals 7, now we have 8 different moduli to choose from. So we choose, say, 6 of them, and we cover 1, 2, 3, 4, 5, and 6 mod 7. So after this stage, we've covered everything except, after prime 2, we've covered everything except 0 mod 2. After 3, we've covered everything except 0 mod 6. After this stage, we've covered everything except 0 mod 30. after P is 7, we've covered everything except 0 mod 210. And we're just going to carry on. And eventually we cover the 0. Okay, so I hope that's somewhat clear. Okay, so these are all different examples of covering systems. And here's an easy proposition. There's lots of them. So we have roughly this many choices. So e to the n to the 3 over 2 over root log n. So just a quick proof. Well, each frame, so for each prime, we take p minus 1 different progressions. So if we take k primes and we take about k squared log k progressions. And we have 2 to the I minus 1 choices for each progression because we get to pick the d. Okay, we pick a divisor of qi minus 1, which was just the product of the first I minus 1 primes. So we have that many covering systems. And how large is that? Well, by the prime number theorem, whatever, this is about e to the k cubed log k. And just substituting what our n was k squared log k, gives the answer. Okay, so some very simple counting tells us that there are this many frames. The first theorem I'd like to tell you about is an answer to Erdős's question that says that this is basically the right answer. So the number of minimal cover systems is some constant times this n to the 3 over 2. So e to the constant plus little o1, n to the 3 over 2 over root log n. So the construction I just showed you of frames doesn't give this constant. To get this constant, you can't use square free numbers. You have to do something more complicated, do some optimization. But the lower bound is sort of similar, but a bit more complicated. You can get an upper bound within a constant factor in the exponent with a relatively short argument, so maybe sort of a couple of pages. But to get the correct constant is quite a bit more difficult. So to do this, we needed to essentially show that, so that morally speaking, a typical minimal covering system looks a bit like a frame. We proved something a bit weaker than that. We showed some sort of rough typical structure result. So if your covering system covers efficiently in some sense, then you can find something that looks like a frame inside it, and then that allows you to count. So the first, perhaps interesting open question is to try and prove a stronger typical structure result for these covering systems. So it seems likely that that almost all minimal covering systems of size n look very much like a frame. We don't know how to prove that, but it perhaps our techniques would be a good starting point for proving such a result. Okay, so that was supposed to be the introduction. So now you sort of have some idea of what frames look like. So let's go on to this extremely famous question of Erdős about whether these things exist with all moduli large. So those in the frames we always use 2. So we haven't found anything so far even that avoids using 2 as a modulus. But you can find these systems, so it's sort of not too hard to find one that avoids 2. Even avoiding 3 is a bit of a challenge. Hough managed to avoid all the way up to start with 9 in 1968. And then this was improved various times. Quickenberg got to 18, Choi 20, Morikawa 24, Gibson 25. That's a big gap between those two. And then in 2009, Nielsen really tried to sort of systematically try to construct these things, and gives extremely impressive construction of a system with minimodulus 40, which uses an enormous number of arithmetic regressions. I'm not quite sure how many, but some enormous number. And he was perhaps one of the first people to suggest that maybe there don't exist such systems. So Erdős, I think, was apparently quite confident that such things existed, just we weren't very good at constructing them. But Nielsen then suggested perhaps not, having tried very hard. she said that the current record is due to Owens, who extended Nielsen's technique to give 42. In the other direction, so the first really significant progress on this problem was made by Filosetta, Ford, Konygin, Pomerantz, and Yu, 2007, who proved the following theorem. If the moduli at least are large and distinct, then the sum of the reciprocals has to grow, at least sort of somewhat fast. So this was, so some evidence in something in the direction of these things not existing. And was also sort of introduced some important ideas that we use later. And they also proved the conjecture of Edge and Graham that I mentioned on perhaps the first slide or second slide, about that if you only use differences between n and constant times n, then you miss a positive fraction. So I'll come back to this later. So this was an important step forward. And in fact, building on their work, Hough resolved the problem with this extraordinary paper written a few years ago, showed that actually you can't. So that you cannot get above 10 to the 16. So there do not exist covering systems with distinct moduli and all moduli at least 10 to 16. So I want to spend perhaps most of the talk, maybe the next 30 minutes, talking about Hough's proof of this result, and also a simpler proof, or a simpler version of Hough's proof that we developed when studying these questions about the density of the uncovered set. So perhaps the main aim of this talk is to advertise this method, because it's very beautiful, and now it's quite simple, and it should have lots of other applications. So I would like to try to explain to you a simple way of proving a slightly weaker version of this. So we'll begin by sketching the proof, and then I'll try and give a sort of extended sketch. Okay, so the idea is going to be that we're going to reveal the arithmetic progressions prime by prime and sort of track the evolution of the uncovered set. That's what I mean by that. So here probability arises. So Hough's key idea was to define a probability measure that sort of distorts the space. If you're going along, we're sort of going to blow up the uncovered region. So try and keep it of sort of positive density in this distorted measure. So we're going to blow up the uncovered set, but we're going to try not to distort too much. We're going to try and blow up the uncovered set as much as possible, whilst distorting as little as possible. So if we can bound the measure in the distorted measure of the covered set in each step, if we can show that the total distorted measure removed is less than 1, then there must be some measure left in the distorted measure, and therefore there must be something left in the real measure, in the uniform measure. Okay, so this is just a very vague way of thinking about what this method is doing, and then I'll try and give the details in over the next sort of maybe 5 slides. Okay, but this sketch is supposed to give you, this is the high level overview of what we're trying to do. And this is the idea which feels like it should have lots of applications, though I don't know of any outside covering systems. Okay, so in order to prove this, I'm going to switch to a more combinatorial or geometric setting. I'm going to prove a more combinatorial statement, and then which is going to imply the result, the number theoretic result. So our universe is just this. We have a bunch of finite sets, and we're going to look at the cube formed by these sets. So QK is S1 cross dot cross SK. Okay, so our universe is Qn. And we're going to be covering Qn with hyperplanes. So what is a hyperplane? A hyperplane just means in each direction you either take a single point or you take everything. Okay. So and we're going to say the set of fixed coordinates of a hyperplane is the points which are not everything. So you should think of the SIs as being like the primes, and then the hyperplanes are like the arithmetic progressions, and the common difference of the arithmetic progression is like the product of the fixed coordinates. Right, and they're parallel if their fixed coordinates are the same, so that'd be the same as two arithmetic progressions having the same modulus, the same common difference. Okay, so this is our world. So we're trying to try to understand coverings of these cubes with hyperplanes with non-parallel hyperplanes. Okay. Right, so to recall this definition of parallel and fixed coordinates. So here's the theorem that I'm going to try to sketch the proof of. So what does it say? It says you have a collection of hyperplanes that cover Qn. So this is like a collection of arithmetic progressions that cover the integers. And no two are parallel, then there must exist one which is only all fixed coordinates are in 1 up to c for some constant c. This can be true as long as the size of the set increases, well, a bit faster than, or linearly with a large constant. So if they're at least 4k when k is large. So for example, if the sk is the kth prime, then this is true. Right? So we're going to prove something. You don't need the things to increase as fast as the primes. You just need them to be bigger than 4k. Okay, and the fixed set all being in 1 up to c is going to be equivalent to, or is going to, would imply that the modulus is bounded. So the modulus, remember, is the product of the size of the sets of the fixed sets. So note this implies Hough's theorem in the case of square-free moduli. Should say that it's not very difficult to extend the proof I'm going to explain to prove the full theorem for the general case. But the details are slightly more technical. It's just some slightly more annoying technical calculations, and so this is a bit cleaner for explaining the method. And what's the proof of this? You just set sk to be 1 up to pk, where pk is the kth prime. Use the Chinese remainder theorem to map progressions into hyperplanes, as I was explaining before. So you can map a progression just by going to this world of this high dimensional world, so each direction is a prime. And that's it. And then it's just basically the same thing. And observing that the primes are at least 4k when k is at least, whatever, 11 or something. Okay, so I hope that's clear. We'll leave that statement up for a second so people can look at it. So right, so we've got these sets. We can try to show that if you cover with hyperplanes, with non-parallel hyperplanes, then there exists one whose fixed set is small in this sense. Okay, so the so I have a picture first. So there are going to be a couple of slides after this which have some definitions or some which are slightly difficult to read. But then after that, the proof will just be 3 very simple steps. Okay, but let me give you a picture first to help you with the definitions. So this is the same picture we had before. So on the base, you have qk minus 1, which is the product of the first k minus 1 sets. The vertical axis is the next dimension, sk. And so in the kth step, we're going to reveal the hyperplanes for which k is a fixed coordinate. So far in the first k minus 1 steps, we've really just been working in qk minus 1. So we've, in particular, we've covered a bunch of qk minus 1. So I've done, these are the gray elements, things we've already covered. And when we extend to sk, then if you've covered something in qk minus 1, then you've covered everything in qk, in that fiber. So I'm going to call these columns fibers. You have a single point in qk minus 1 cross sk. Okay, and then in step k, we're going to introduce hyperplanes for which k is the maximal fixed element. So because k is a fixed element, then it looks like this. So because it has no larger fixed elements, we can think of it as being a subset of qk, rather than Qn. And because K is a fixed element, then it lies a subset of a single row of this, this two-dimensional picture. Okay, so all, and I've drawn it as an arithmetic progression, but really it's a hyperplane in this hyperplane where we fix this element of Sk. So this is really is a high-dimensional picture that I'm unable to draw because I'm not very good at three-dimensional pictures. Apologies, or d-dimensional pictures, whatever, k-dimensional, I guess. Yeah. But anyway, so this is what you should think of it. This is what you should think of it as looking like. And then maybe there's another arithmetic progression there, another one there, and maybe that's all it is. Okay. So then this gives us the new gray set in QK, which is all the gray plus the black circles. And then in the next step, we'll reveal Sk minus Sk plus 1, which will give us an extra dimension. Okay, so I hope that picture is somewhat clear. So let me give the next slide. So this is the distortion method. So we call this the distortion method, which was really introduced by Hough. Though the version that I will be describing is our simplification of this method. Right. So what are we going to do? We're revealing the hyperplanes in n rounds, so corresponding to the maximum fixed element. We define a sequence of probability measures that gradually distort the space. So P0 will be the uniform measure, and in each step we'll just distort the measure a little bit more. In a well-defined in a second. Okay, so the measure will just depend on the hyperplanes with all fixed elements at most k. Okay. Right, and our hope is to choose it so the distorted measure of the covered set is small. Okay, that's gonna be our aim. So we need to try and keep these two following things in mind. We don't really want to change the measure of the already covered point, the total set of already covered points, because we want to sort of keep track of that. Those covered in the previous rounds. And we don't want to increase the measure of any set too much. We don't want to distort the measure too much. So to do the first of these bullet points, we'll just make sure that on each fiber, we'll keep the same amount of measure that we had before. So remember a fiber in the previous picture with these vertical lines. So there's some measure on QK minus 1. And if we just extend that measure to the fiber, so we'll make sure that each fiber gets the right amount of measure. Okay, so we're just going to push the measure around inside the fibers. Okay. And right, in the second one you'll see in a second. So right, so given a probability measure on QK minus 1, so a natural thing to do to try to make the measure of the covered set small would be just to put the measure to be 0 on the covered set, on the things that you've newly covered, and then redistribute uniformly on each fiber. And this is basically what Hough did. And this has the advantage, it doesn't change the measure of the already covered points, but it can increase the measure of some sets by quite a lot. So it distorts the measure a bit too much. So, all right, sorry, and then it just redistribute the removing measure within fibers, so keeping it constant within fibers. Okay, so it turns out that it makes the proof a lot simpler to do something a little bit more complicated. Okay, so there's the first thing you might try to do. This is the thing that Hough did, and it worked, but required the proof is really quite complicated. You need some additional very clever ideas to make the proof work, and actually it turns out that you can do something a bit simpler. So, okay, so here is what we actually do. So the key definition on this slide is alpha k of x, which is just the proportion of the fiber corresponding to x that's removed in step k. So each fiber is a column, remember this picture. So there's a fiber for each x in qk minus 1. And this is just the proportion of the fiber that's removed that's covered in round k. Okay. And what are we going to do? Well, we're going to fix some delta. I'm sorry, not define alpha k. That was the wrong thing to say. Define pk xy. Sorry, oh, it's a typo. So if alpha is smaller than delta, then we just do what Hough did. We put the measure to be 0 on the covered element and redistribute the measure proportional. So on the rest of fx, sorry, on the rest of the fiber. Okay, so on a particular fiber, if we reduce a little bit, we put 0 there and then bump everything else up a bit to keep it constant on the fiber. However, if x is bigger than delta, then we don't want to do that because that would distort the measure too much. So all we do is we increase the measure on the uncovered set by a little bit and decrease the measure on the covered set by a corresponding amount. So instead of going to 0 and whatever, we cap the amount of distortion we allowed, and then we just do the best we can given that cap. Okay, so something very simple. Okay. So this has the advantage of, because we don't distort the measure too much, we sort of keep the independence between rounds. So the big picture of why Hough's theorem is true is because different primes, because they're sort of perpendicular to each other, then the arithmetic progressions are sort of independent. They act in sort of independently of each other. And so each one is sort of supposed to cut out about the same amount as it would if it were random. But it's not true in practice, but by distorting the measure, we can make it more true. By not distorting the measure too much, we also keep it true. Okay, so that was a bit technical, but now the difficult part's over, and now everything is very simple. Okay, so what's the key lemma? The key lemma is this very simple statement. It's that take any collection of hyperplanes, if the sum of the second moments of these alphas in the measure, the current measure, so with respect to the k minus 1 measure, if the sum of those is less than 1, because they're normalized by this 1 over delta 1 minus delta, then you don't cover. And the proof is incredibly simple. So you do a very simple calculation that just uses this very advanced inequality, max a minus b and 0 is at most a squared over 4b. And so it's basically the second moment method. And you get this inequality that the measure of bk is the set of points that we've removed in step k. So we've covered in step k. The measure of that set with respect to the kth, in the kth measure, is just at most this expectation of alpha squared over 4 delta 1 minus delta. Okay. And now we use this second fact that the measure is not changed by later steps. So Pn of bk is equal to pk of bk. Right? Because we kept the measure on a fiber constant, then we have this equality at the bottom of the screen, because the sum of by the assumption, the sum of pk of bk is less than 1. So just by the union bound, the total measure removed in the final measure is less than 1. So the remaining measure is positive. So something is left. Okay, so it's just an incredibly simple argument. Okay, so you can see that the delta has come in here, that if you take delta smaller, then this bound is getting worse. But in the next lemma, you'll want to take delta smaller. So there's some balance in choosing the optimal delta. Okay, so I hope this is clear. So this is the key lemma, and the proof is really just a few lines. Okay, so right, so we just need to bound the second moment. So here's a lemma that does that. So the second moment is at most. So the main term here is this 1 over sk squared. and then this product is you can think of as being an error term. And the error term you'll see involves delta. Okay, so when you make delta larger, then this error term gets larger. Okay, and the proof of this is also very simple. It maybe takes a couple of pages. Let me just give you a sketch of the proof. It's not difficult at all. So it's two sort of fairly straightforward. It's a simple calculation. So you can bound the pk measure of a hyperplane just using a simple induction, and you get this product of 1 over 1 minus delta size of Sj for all the fixed elements of the hyperplane A. So you only lose a term when things are fixed. And then given this, you just take a union bound, and you're done. Okay, so this 3 comes in from this union bound. So there's a 3 to the k in choosing. So we have to apply this, because we've had a second moment, to the intersection of pairs of hyperplanes. And because we have the intersection of pairs of hyperplanes, then there are 3 to the k choices or whatever. So that's where the 3 comes in the bound. Okay, but it's a very, very simple argument. Okay, but now we're done. So we proved the key lemma that was super simple. We bounded the second moment that was super simple. And now we can prove the theorem. So I've stated it in a slightly more precise way here. So with the SK just needs to be at least 3 plus epsilon, and the constant depends on epsilon in this case 0. So it's the proof. So that the bound on the second moment. Just a very simple calculation, just a few lines, gives you that this is, so if you're summing this over things larger than C, then it's big O of k to the minus 1 plus epsilon. So the minus 1 plus epsilon is because S size of Sk is at least 3 plus epsilon. And plus, let's go back to this lemma, which is the 3 over the size of Sj. So this product is small. This is summable. Constant go depends on epsilon k0. So this is small as long as C is sufficiently large. Okay. Moreover, if we don't have a hyperplane, fixed elements are all small, then alpha k of x is 0 for all of those, because we didn't introduce, remember, in each step, we only introduced the hyperplanes. Alpha k only depends on the hyperplanes whose fixed set elements are at most k. So if nothing is contained in the first C, then you just get 0 for the alphas for the first C, so they don't add anything to this sum. So by the key lemma, we don't cover. And that's the entire proof. Okay. So this proves Hough's theorem in the case of square free moduli, in fact, a stronger sense, because you only need the case where the SKs are size pk, so they would grow at a rate k log k instead of just linearly. This argument gives a worse constant than Hough obtained, but a more complicated version of the same method. You're just more careful with choosing the deltas well, you're quite a lot more careful. By being quite a lot more careful, we were able to get the bound down to 10 to the 6. So in Hough's theorem, he proved 10 to the 16, so we were able to get down to 10 to the 6. So the bounds are now 42 from below and something like 600,000 from above. Okay, so just to finish, if there are no questions from me from that part, I'd like to go to the third topic, the last 10 minutes or so, which is about the density of the uncovered set. So recall the question of Erdős. This was introduced by Erdős and Graham in 1980. So they asked if, they asked, made a conjecture that was proved by Philosetta, Ford, Conjugan, Pomerance, and Yu, who in the following stronger sense. They showed if n is large compared with c, in the following sense, a bit bigger than polynomial, then any set of arithmetic progressions with differences between n and constant times n, the uncovered set is not only has positive density, but it has the correct density. So the density that you would get if you just chose the progressions randomly. So the same as saying that basically you basically can't do better than choose the progressions randomly if you're choosing them from this set n up to constant times n. Right. And notice this is bounded away from 0 because the sum of the reciprocals, sum of 1 over di is bounded by whatever it is, log c. Right. So motivated by this theorem, they ask the following very natural and beautiful question. So is it enough just to bound the sum of 1 over di? So can you get a similar theorem whenever you bound the sum of 1 over di? So here's the question. So suppose the differences are all large and the sum of 1 over di is bounded. Is a positive proportion of the world uncovered, a positive density uncovered? So we started thinking about this, and we tried to prove this for quite a while, using trying to extend Hough's method to prove this, before realizing actually it's false. So the answer is no. In the following very extremely strong sense, so really surprisingly strong. So even with c equals 1, so for any m and any delta, there's a collection of progressions who have no chance of covering, because just the total volume they cover is less than 1, but they cover almost everything. They cover all but less than delta. So to do this, you need to use very large primes. Basic idea is to cover randomly at some point, and then take all the product of the primes you've got so far, and then all future things will be multiples of that product, and then continue and iterate this lots of times, and it works. Okay, so this was it was an incredibly natural question, but unfortunately it was the wrong condition. So what is the right condition? So here is the theorem. So we're going to replace the 1 in 1 over di by something a little bit bigger. So we're going to replace it by the following multiplicative function. We're calling chi here, which is just, so for each prime, we put chi of p to the I being this 1 plus log p to the 4 over p, something a little bit bigger than 1. And then it's multiplicative, so, right. So for non-prime powers, it's just you take the product. Okay, and if the sum of chi of di over di is bounded, then the density of the uncovered set is positive. So this is sufficient. So I put this near the end because it's I understand it's a bit more technical. But right, so we're just replacing. So 1, if you replace chi by 1, then the conclusion is false. And actually, even it's sharp in a much stronger sense. If you replace chi by something in the form 1 plus large constant over p, then it's also false. So you can also find a set of progressions with arbitrarily large distinct moduli, which cover almost all the world, all but little O1 proportion, and C is bounded. Okay. So this is really the right scale. So this the correct scale. So this really is the correct form of the statement, and the correct scale is that with the correct chi is something between 1 plus constant over p and 1 plus polylog over p. So I think it'd be very interesting to determine the correct behavior of this. So we don't have a conjecture. Perhaps I was forced to guess. I might guess that that it's close to constant over p. So some pretty slow growing function. I mean, maybe even as soon as it goes to infinity, then it's so as in if it's 1 plus something that tends to infinity over p, maybe it's already true. And this was proved by the method that I described in the middle of the talk. So by a more complicated version of that method. So not using the same delta in each step, and here we're not square free, but essentially the same method. So this very simple distortion method seems to be very powerful, at least in this setting. And so the main takeaway I'd like from the talk is that surely a method that works so well in this setting should have other applications. There should be other things one could do with it. So I would be very happy if people found some other applications. Okay, so I'm actually almost done, a little bit early. I'd be happy to learn. So here are a few additional consequences. So here's a conjecture of Schinsel from how long ago? It's like more than 50 years ago. So in any covering system, one of the moduli divides another. That's a very natural conjecture, and it's true, and the method is strong enough to give it. So as well as being simpler, so our variant of Hough's method is not only simpler, it's also a little more powerful and but more flexible. So we're going to do this. So another famous question is the question of Erdős and Selfridge. So does there exist a covering system with all moduli distinct and odd? Or can you avoid all multiples of 2? It turns out that this problem, it doesn't look like it, but it would imply the theorem above. So it's stronger, strictly stronger than Schinsel's conjecture. Unfortunately, we're not able to prove it. So Hough and Nielsen used Hough's method to get a long way towards proving it. They showed that either you have a multiple of 2 or a multiple of 3. This was published just last year. So we can improve that a bit. We can show that either you got a multiple of 2 or a multiple of 9 or a multiple of 3 and a multiple of 5. Okay, so this pushes a little bit more towards the conjecture. It also gives a very short proof of this theorem of Hough and Nielsen. So it's strange that this feels like you're almost all the way there, but actually for our method, this is it's very quick. By working a lot harder, you can get this improvement. But getting all the way to the full conjecture or answering the full question seems the method is not strong enough. However, with other consequence that for square free moduli, we can prove that you need to have some multiple of 2. This is actually it's quite a lot more complicated. This requires another maybe 5 or 10 pages of work and quite a lot of computer power to prove. Anyway, so this Erdős Selfridge problem is still open. Okay, so I'll stop there. Thanks very much.
Great, thank you, Rob, very much. Maybe let's open it up to questions. So we'll do some applause in a minute. So there are ways of raising your hand. So if in the, I have to figure out how to do this. Yeah, so at the bottom of the screen under reactions, you can raise your hand. I'm doing this now. Let me start by asking a question. So what do you think the prospects are for the Erdős Selfridge problem?
Sorry. I missed it. Sorry.
What do you think the prospects are for attacking the Erdős Selfridge problem? You've gone this enormous distance. It's
right. So it seems like there's an extra sort of significant idea needed. That the method So we tried reasonably hard to optimize it, and it seems like it's really not quite strong enough. I mean, it's not completely obvious that the answer is that they don't exist. Though, I mean, I suppose that's what I would guess. It may just be that one needs a relatively simple idea, but yeah, it's very unclear to me. It's very unclear how big an additional idea one needs, but certainly some additional idea is needed.
Other questions? Oliver?
Can you hear? Is this working?
Yes.
Yeah.
Hi, hi, Rob. Yeah, thanks. That was very nice. Maybe two things. So your thing about limiting the distortion, the point where that came in was when you had this bound on the measure of one progression on page 99.
Yes.
Is that right? That you had a very simple bound that it's at most this product of 1 over the 1 minus delta thing.
Exactly.
Whereas in Hough's thing, he has some.
Yeah, he has to do something much more complicated. He goes in quasi-randomness, and yeah, it's extremely clever. But
Okay.
Yeah,
Okay. Yeah, and I guess the other thing is there's things that are much more complicated. Is that sort of kind of calculational complication? So you've shown us the rest of it, like do the same but different delta, and you have to find exactly the right formula and so on. Or is there?
Yeah, there's some. Yeah, there's some ideas, but mostly it's calculation.
Okay.
So you have to think a bit about where. So there are some ideas in the calculation. So how to do the calculation more.
Yeah. That's...
Also, there's some sort of some lemmas that one needs to prove to deal with sort of the initial section. But yeah, not difficult ideas.
Okay.
Yeah. So yeah, most of the really interesting part, I think, is not that. It's just the general method.
Okay, thanks.
Okay, other questions?
Right. So the question was whether there are natural questions in other groups other than Z, and it seems quite reasonable that there should be. But it seems like an extremely good question, in fact, that I haven't thought about at all. So I don't have a very good answer for it. I'm sorry. If anyone has a suggestion for a question, then perhaps we could discuss it. I can't think off the top of my head what the correct question would be. It seems to me like an extremely natural and very good question.
Okay, if anyone has another question, you can now unmute yourselves. So we've opened that up.
Hi, I was wondering, so if we consider sort of, so we have this sort of lower bound of 42 and this upper bound of 10 to the 16. For the lower bound of 42, is it known that you can do it for every number less than 42? So
yeah.
Okay, I was just wondering, do we know we can do it for 41 or something like that as well?
Do we know that there where the minimum is equal to 41?
Oh no, I was wondering sort of if so I thought so for that there was a covering system with distinct moduli difference at least 42.
Yeah, right. Where the minimum equal to 42. Yeah.
But I was wondering whether it was known if if for each number less than or equal to 42 that we can find a system with that minimum modulus.
I suppose you can do it trivially by adding that one on, right? So if you don't require it to be minimal as well.
Yeah.
Yeah. So it's a cheating way. If you require it to be minimal, then I don't know the answer. I haven't looked at Owen's paper, so I don't know whether he does it for 42. I suspect not. I suspect he just finds one with 42. So I suspect the answer is no, if it's minimal.
Sure.
Yeah. So I think it'd be interesting to. Right, so there's lots of things we don't understand about these things. So I think it still is an interesting question to understand a bit better exactly what one can say about these systems with large minimal modulus. The most interesting question was solved by Hough, but I think these things are still poorly understood, and so I think these still sort of valuable things to think about.
Hi, Rob, and everyone. This is Julian. But I was just saying, I wanted to say that I think there is a non-abelian version of this, which I don't know and perhaps can't state perfectly. But it's just something like, can you cover an arbitrary group with with cosets of distinct subgroups? And I believe this is still open. I don't remember the name of this connection.
So the question is whether you can the question is whether you can do this for every group with a notion that the subgroup has to be large.
Yeah, I don't exactly know what the condition on the group is, but it's something. I guess there's something there that you need. Right. Exactly.
Okay. Is this written down somewhere? Do you know?
Yeah. Yeah, it's like a known thing. I don't know if. Okay, I'll just see if I can remember what it's called.
Okay. Yeah. Okay, so that was a better answer to David's question.
Okay, if there are no
any other questions while Julian is remembering.
Okay, so maybe this is a good point to thank Rob. So thank you very much, Rob, for a beautiful talk. Thank you to everybody for coming. So and bearing with the odd internet problem and the odd problem with the hosts. But we'll carry on next week with Luigi Adariaberi and possibly one other speaker as well. So thanks very much, and yes, and stay well. So see you next week.